This is section 11.4 on finding the area of regular polygons. And to start off with, we're going to look at a few warm-up problems. The first one is to find the area of this triangle, and we're given one angle. So since we have a 30, 60, 90 triangle, I see that 24 is the long leg. So if we divide that by root 3, we can get to the short leg. 24 divided by root 3, when you rationalize it, comes out to 8 root 3. And then to go from the short leg over to the hypotenuse, we would multiply that by 2. So x would be equal to 16 root 3. In the second problem, I see it's another right triangle. This time we have a 72-degree angle, and 72 degrees isn't special to us, so we're going to use trig. 10 is the opposite, y is the adjacent. So my equation would be that the tangent of 72 degrees is equal to the opposite over the adjacent. Now algebraically, we would multiply both sides by y, divide both sides by tangent of 72. So y is equal to 10 divided by the tangent of 72 degrees. There's our exact answer. You can go to your calculator and get the approximate decimal. In this third one, it's a 45, 45, 90 triangle. So to get from z to one of the legs, we would get smaller. We would take 6 and divide it by square root of 2. And then when you rationalize that, you'd get that z is equal to 3 square root of 2. Now we're going to look into finding areas. And in this one, we have a regular triangle. The altitude, which would also be one of the medians, or angle bisector, perpendicular bisector, is 8. So I'll go ahead and draw it right onto the triangle. And by drawing this, because of all the symmetry, we have a 30, 60, 90 triangle because the left is congruent to the right. 8 is the long leg. If we divide that by root 3, that'll get us to the short leg. So this is 8 over root 3 for that length, which means the entire length would be double that, or 16 over root 3. And if we rationalize that, we'd get that one of the sides is equal to 16 root 3 over 3 for the entire side right there. So now our area is 1/2 times that base, 16 root 3 over 3, times the height, which was 8. Now if we multiply all the numerators, divide by the denominator, we can simplify this one a little bit. 16 divided by 2 is 8, times that 8 would give us 64 root 3 over 3 for the area in this one. Again, that's the exact value. You can go to your calculator to get to the approximate decimal. Next example, we have a regular hexagon, and regular hexagons are actually just as special as those regular triangles. If we were to draw in these diagonals that go to opposite vertices, we would get this. Each one of those triangles is congruent to each other, again, because of all the symmetry. And in a regular hexagon, each angle is 120 degrees. This diagonal is going to bisect that, giving us 60, 60, and 60. So this is made up of 6 equilateral triangles. Each side is equal to 14. So if I just focus on this triangle right here, I could find the area of it and multiply by 6. So I'll draw in that length. That made this left side here into a 30, 60, 90 triangle. 7 would be the short leg, and then the long leg would be 7 root 3. So the area of this yellow triangle is 1/2 times the entire base of 14, it's the whole yellow triangle, times the height, which is 7 root 3. Now if we simplify this, that would come out to 49 root 3. And I want to make sure that I'm careful what I'm talking about. This is the area of just that triangle, so I should show my work for that, which means then that the area of the hexagon, which is what we want, is 6 times bigger than that. So I could take 49 times the 6 to get 294 root 3 for our exact area. You can go to the calculator, multiply that to get your approximate decimal then. Here's our next example. We have a regular triangle. The distance from the centroid to a vertex is 6. And because this is a regular triangle, it's a centroid, it's an in-center, circumcenter, it is everything, which means it has some special properties about it. If I were to extend that length, this segment would not only be a median, it would also be a perpendicular bisector, but a median has, or where the medians intersect would be the centroid. Centroid has a 2-to-1 ratio, so if this length is 6, the other length is going to be 3, which means the entire length of that altitude would be 9. I'm using these terms interchangeably, again, because of all this symmetry. And in this yellow triangle, we have this length is 9, right triangle, and it's going to be a 30, 60, 90 triangle. I know that because this was 60 degrees from the regular triangle. 9 is the long leg. So if we divide 9 by root 3, we get that this length is equal to 3 root 3. So if we double that, we'd get one entire side of the regular triangle to be 6 root 3. And there's many ways to finish off a regular triangle. We're going to go with this one. Each side is 6 root 3, so if we take that, square it, times root 3 over 4, that's a nice formula for us. So we want to take 6 root 3, square that value, multiply by root 3, also divide it by 4, and that would give us then 27 root 3 for an exact area. Next one, we have a regular octagon with a radius of 10. I'm not great at drawing regular octagons, but I can draw 3 consecutive sides of it, knowing that eventually there'd be a total 8 of them to close it off. When it says the radius is 10, that means from one of the vertices to the exact middle of that regular octagon has a length of 10. And I'll draw in another one. That length is going to be 10 also. And in this regular octagon, there would be 8 of these triangles going around the middle point of this regular octagon. And all 8 of those regular triangles would be congruent. All of these central angles would be the same. And if I take 360 divided by 8, I find out that that angle is going to be 45 degrees. I can find the area of this one triangle by doing 1/2 times 10 times 10 times the sine of 45 degrees. Simplify that a little bit and we get 50 times the sine of 45 degrees for the area of that one triangle. And since this is a regular octagon, I already mentioned that there's going to be 8 of those. So if we multiply this value by 8, we would get 400 times the sine of 45 degrees for an exact area. Now there's definitely other ways you could do this one. We could have split the triangle in half, found the area of this one triangle by taking half of one of the interior angles. We could have split it up into other shapes as well, but whatever this approximate answer is should be equivalent to any other answer you get. Next one. As I said a couple times already, there's more than one way to do these problems, and I'm going to show one way that's really going to build it into a general formula for regular polygons. So this is a regular pentagon, and its perimeter is 40, which means 40 divided by 5. Each side is equal to 8. I can put 8s all the way around. Or when I go to the exact center, and this would be the intersection of different diagonals, this distance is the same no matter which vertex you go to. I have this segment, I can draw in this segment. That creates an isosceles triangle congruent to all these other isosceles triangles. In a regular pentagon, each interior angle is 108 degrees. That's a formula from before, n minus 2 times 180 divided by n. This whole angle was initially 108 degrees. Because this radius is bisecting it, that would give us 54 degrees, 54 degrees, and then 36 degrees up at the top. Back 72 degrees to the top. But I'm going to focus on this one triangle down here at the bottom. Draw in this altitude, and I'm going to call this length x and call this length y. The original side of the pentagon was 8, and because this x is really half of that, I can call this 4, and I want to find the value for y. In this right triangle, we could use trig, so the tangent of 54 degrees is equal to opposite over adjacent, multiply both sides by 4, so then this is going to be the length of y. That's the altitude of this triangle. Oops, I erased a little bit too much. It's also the altitude of this triangle. So if we found the area of this yellow triangle, we could then multiply that by 5 to find the area of the entire pentagon. So we'll go there. Area of that triangle is 1/2 times the entire base, which isn't just 4, it's 8, times the y value, which is 4 times the tangent of 54. Now that's that triangle I could multiply and simplify here, but again, my goal in this problem was to build onto another formula. If I wanted the area of the entire pentagon, I would take this and multiply it by 5. Because multiplication is commutative, I can multiply the 1/2 or the 8 or this 4 times 5. Doesn't matter where. I'm going to choose to multiply it right in the middle. Take the 8 times 5, so it's 1/2 times 40 times 4 times the tangent of 54. And I want to look at this equation I have now in terms of parts. The 1/2 is in it because that's the area of a triangle, 1/2 BH. The 40 represents the perimeter of the original regular pentagon. And the 4 tangent of 54 is the distance from the center of the regular polygon to the middle of one of the sides. It's the distance to each one of those sides. It's the shortest, it's a perpendicular distance. We call that the apothem. Okay, so now at this point I have this written down. We can multiply these numbers, and that would give us 80 times the tangent of 54. And if you multiply that together, you'll get a decimal, which should be equivalent to any other way of doing this one when you look at the approximate answer. That gives us a general formula. In a regular polygon, the area is always equal to 1/2 times the perimeter times the apothem, or the apothem. It's commutative, so we could switch the order of this. This only works if it's regular, but anytime you have a regular polygon, you can use this formula to break it down for us a little bit. And I showed it why this worked in the last one, because eventually you're going to be finding the area of each one of these triangles, and you have the entire base of one of these triangles multiplied by the number of sides. So this times the number of sides is essentially the perimeter. And the apothem of the entire regular polygon is really just the altitude of one of those single triangles. This is a formula we can use when we have regular polygons. Now, having just gone over that formula, I see I have 2 regular polygon problems here. And I could choose to use that formula or not, depending on what I see as the most efficient way to do the problem. Regular hexagons are special. They're not just a regular polygon, they're one of the few special regular polygons. So I'm going to come back to this one later and use a separate formula. In this one, a regular decagon where the apothem is equal to 13. So here are 3 adjacent sides of our regular decagon. It would keep going. The apothem is equal to 13. I can put that in there. Draw in a radius, because my goal now is to figure out the perimeter, and then I have 1/2 perimeter and apothem. In a regular decagon, we can do n minus 2 times 180 to get that the sum of the interior angles is 1440. Divide that by 10 to see that each angle in our regular decagon is 144 degrees. But when this radius is drawn in, that gives us 72 degrees. I'm going to use trig to find that value of x. The tangent of 72 is equal to 13 over x. With a little bit of algebra, we get that x equals 13 over the tangent of 72. Now to get the entire perimeter, we're going to have to take x and multiply it by 2 to get one complete side, multiply it by 10 more to get all 10 of those sides. So in essence, we're multiplying this by 20. When you multiply a fraction by a number, you're really just multiplying the numerator. So the entire perimeter now is 260 over the tangent of 72. So now using that formula that I just talked about, we have 1/2 times our perimeter times our apothem, and we can multiply the numerators. 260 times 13, divide that by 2, and we're going to get 1690 over the tangent of 72, and then use our calculator to get that as an approximate. Last problem here, regular hexagon with each side equal to 12. I could do the 1/2 PA again, or realize that if each side of this is equal to 12, and in a regular hexagon it's made up of a total of 6 regular triangles, I could find the area of one of them and then just multiply by 6. So 12 squared root 3 over 4 would be the area of one, multiplied by 6. So we're just looking at the numbers here. Take 12 squared, multiply it by 6, divided by 4, and we're going to get 216 root 3 as a quick way to find the area for this one. As always, there's more than one right way, but that's a nice quick way for that one.